In the late 1970s and early 1980s, commercial aviation operated under a carefully cultivated assumption that redundancy, when layered deeply enough, could neutralize almost any conceivable failure. This belief was not naive. It was the logical outcome of decades of empirical learning, hard-won through accidents, metallurgical breakthroughs, and increasingly conservative certification standards. By the time the McDonnell Douglas DC-10 entered mature service, the industry considered the probability of a complete loss of aircraft control to be vanishingly small. Not impossible in theory, but statistically absorbed by layers of engineering safeguards. The aircraft that would later operate as United Airlines Flight 232 was conceived inside this paradigm of confidence. The DC-10's design philosophy was unapologetically systems-driven. Every critical flight control relied on hydraulic power, and every hydraulic circuit was treated as an independent lifeline. Three separate hydraulic systems, numbered 1, 2, and 3, ran through the airframe, physically separated where practical, each pressurized by engine-driven pumps. The loss of one system was a non-event. The loss of two was considered an extreme but survivable abnormality. The simultaneous loss of all three was treated as a theoretical impossibility, not because it violated the laws of physics, but because it violated the assumptions of spatial separation and failure independence embedded in the design certification logic. At the heart of this confidence was the tail-mounted engine, the General Electric CF6-6D, installed at the base of the vertical stabilizer. Its location offered aerodynamic efficiency and redundancy against asymmetric thrust, but it also imposed a unique architectural constraint: the routing of hydraulic lines. All three systems, despite being logically independent, passed through the tail section in close proximity as they fed the elevators and rudder. This routing was accepted because the probability of a single event capable of severing all three lines was deemed negligible. The vertical stabilizer itself was treated as a robust structural firewall, capable of containing localized failures and preserving overall structural integrity. The CF6 engine represented the pinnacle of high-bypass turbofan engineering of its era. Its fan and compressor stages generated enormous thrust with unprecedented fuel efficiency, while its high-pressure turbine operated under extreme thermal and mechanical loads. The first stage fan disc, forged from titanium alloy, was designed to withstand tens of thousands of fatigue cycles, each cycle defined by the microscopic expansion and contraction induced by rotational stress and thermal gradients. Titanium was chosen for its high strength-to-weight ratio and corrosion resistance, but it carried an inherent vulnerability: sensitivity to subsurface manufacturing defects that could remain invisible for years. Within the manufacturing process, the fan disc was produced through a series of forging and machining steps intended to align the metal's grain structure and eliminate internal voids. Non-destructive inspection methods, primarily ultrasonic testing, were applied to detect inclusions or cracks. However, inspection technology of the time operated within resolution limits. A microscopic flaw, on the order of a few millimeters, could escape detection if its orientation or acoustic signature fell below the sensitivity threshold. Such a defect would not compromise immediate performance. Instead, it would become a seed embedded deep within the metal, waiting to be activated by repeated stress. This is where the illusion of safety becomes most instructive. The DC-10 was not unsafe by contemporary standards, it was exemplary. Yet safety, as defined by certification, is always bounded by what engineers believe to be credible. The fan disk's fatigue life was calculated using conservative stress margins, assuming homogeneous material properties. The hydraulic system routing was approved based on the assumption that engine failures would remain contained within the nacelle or disperse debris in predictable trajectories. These assumptions were reasonable, statistically defensible, and fully aligned with the knowledge of the era. They were also wrong in one critical respect. They underestimated the compound risk of material failure interacting with system architecture. On July 19, 1989, United Airlines Flight 232 departed Denver en route to Chicago, carrying passengers, crew, and cargo through the routine geometry of domestic air travel. At cruising altitude, the aircraft existed in a state of dynamic equilibrium. Aerodynamic loading on the control surfaces was balanced by hydraulic pressure, thrust, and trim. The fan disc in the tail engine was rotating at several thousand revolutions per minute, its rim experiencing centrifugal forces measured in tens of thousands of pounds. Each revolution slightly opened and closed the microscopic crack buried within the titanium, advancing it by an almost immeasurable amount. This slow propagation is the defining characteristic of high-cycle fatigue. The crack does not announce itself. It does not distort performance parameters or trigger vibration warnings until the remaining intact cross-section of metal becomes insufficient to carry the applied load. At that moment, failure is instantaneous. The stored kinetic energy within the disc is released violently, converting rotational momentum into radial fragmentation. Containment rings are designed to absorb this energy, but they are engineered against known failure modes, not against worst-case scenarios involving near-rim fractures at full rotational speed. When the fan disc finally failed, it did not fragment benignly. Large sections of titanium escaped the engine casing with ballistic energy, behaving less like shrapnel and more like high-velocity projectiles. These fragments severed hydraulic lines in the tail with surgical efficiency. In a fraction of a second, systems 1, 2, and 3 lost pressure simultaneously. Hydraulic fluid atomized and vented into the airstream, leaving the aircraft with no powered control over elevators, ailerons, or rudder. What remained were secondary effects: differential thrust, aerodynamic drag, and the inherent stability or instability of the airframe itself. The significance of this moment lies not in the drama of the explosion, but in the collapse of an assumption. Redundancy failed not because it was insufficient in quantity, but because it was insufficiently independent. The architecture of confidence assumed that failures would be isolated. The reality demonstrated that a single material failure, born decades earlier in a forge, could couple with system layout to produce a common cause failure of unprecedented scope. At this point in the narrative, the aircraft was still structurally intact. The wings were producing lift, the fuselage maintained pressurization, and the engines on the wings continued to generate thrust. Yet the airplane had been transformed from a controllable system into a marginally stable projectile. Aerodynamic forces now acted without mediation, and every change in speed or attitude introduced nonlinear responses. The design philosophy that had once promised safety through redundancy had reached the boundary of its predictive power. This is the architecture of confidence in its purest form, a machine built to survive almost anything, undone not by neglect or recklessness, but by a rare convergence of material failure, fatigue physics, and architectural assumption. It is within this convergence that the true forensic significance of United 232 resides, not as an anomaly, but as a lesson in the limits of engineering certainty. As the aircraft settled into cruise, the environment around it appeared benign by every conventional metric. Atmospheric conditions along the route were stable, with no convective weather imposing abnormal aerodynamic loading on the airframe. The DC-10 was operating well within its certified envelope, trimmed for efficiency, its control surfaces deflected only marginally to maintain level flight. From the cockpit, the machine presented itself as healthy. Engine parameters were nominal, vibration indicators quiet, fuel flow balanced. Nothing in the data stream suggested that the aircraft was approaching a state of irreversible instability. Yet the absence of external stressors did not equate to the absence of internal stress. Inside the tail-mounted CF6 engine, mechanical forces accumulated relentlessly. The high-pressure turbine transferred energy downstream, sustaining fan rotation through a shaft subjected to torsional and axial loads. The fan disc itself experienced the most punishing regime: extreme centrifugal stress combined with thermal gradients imposed by climb, cruise, and minor thrust adjustments. Each adjustment, however small, constituted a load cycle. Over years of service, these cycles accumulated into the tens of thousands, incrementally advancing the subsurface crack embedded within the titanium alloy. This type of defect propagation follows no linear timeline. Crack growth accelerates as remaining material cross-section diminishes, increasing local stress intensity. The process remains invisible to cockpit instrumentation because it does not affect rotational balance until the crack reaches a critical length. Vibration sensors are tuned to detect gross imbalances or bearing failures, not the silent elongation of a fracture front buried beneath the surface. The engine, from a systems perspective, remained functionally perfect until the precise moment it ceased to exist as a coherent structure. While the engine approached this threshold, the airframe continued to respond predictably to aerodynamic forces. Lift distribution across the wings was symmetrical, and the aircraft's longitudinal stability relied on small elevator inputs mediated by hydraulic actuators. These actuators, powered redundantly, were designed under the assumption that hydraulic pressure would always be available from at least one system. The control laws of the aircraft were not adaptive. They were mechanical and hydraulic, predicated on the continuous availability of pressurized fluid. Without it, the control surfaces would float freely, driven only by aerodynamic hinge moments. The routing of the hydraulic lines through the tail represented a compromise between structural efficiency and spatial separation. Engineers minimized weight and complexity by clustering lines where they converged near the empennage. Protective shielding was incorporated, but shielding itself was optimized for plausible failure modes, contained engine failures, limited debris dispersion, and localized structural damage. The design did not account for high-energy fragments exiting the engine casing at trajectories intersecting all three systems simultaneously. This was not negligence. It was a boundary condition deemed statistically irrelevant during certification. As the fan disk approached failure, the aircraft was subjected to subtle but increasing vibratory energy transmitted through the engine mounts into the tail structure. These vibrations remained within allowable limits, blending into the background mechanical noise of flight. The crew had no sensory indication that a catastrophic material failure was imminent. The airplane's behavior reinforced the illusion of safety created by decades of reliable service and by the inherent conservatism of commercial aviation engineering. When the fracture finally reached critical length, the transition from stability to chaos occurred faster than human perception could resolve. The fan disk disintegrated under centrifugal load, releasing fragments with velocities exceeding the speed of sound. These fragments followed ballistic trajectories dictated by rotational vector, casing geometry, and instantaneous failure orientation. Several pieces penetrated the engine casing and exited the tail structure, slicing through hydraulic lines with minimal energy loss. The severance occurred nearly simultaneously, collapsing pressure in all three systems within seconds. The immediate aerodynamic consequence was profound. Elevators lost hydraulic authority and defaulted toward neutral under hinge moments. Ailerons became unresponsive, their deflection frozen by aerodynamic loads and residual friction. The rudder, critical for yaw control, also lost actuation. The aircraft was no longer a pilot-controlled system, but a dynamically unstable body responding solely to thrust asymmetry, drag, and gravity. The environmental forces acting on the airframe now operated without correction. Small perturbations in pitch resulted in divergent oscillations known as phugoid motion, where the aircraft alternately climbed and descended, exchanging kinetic and potential energy. Normally damped by elevator inputs, these oscillations now grew in amplitude. Roll stability degraded as asymmetric lift emerged from minor variations in wing loading. Yaw stability became unpredictable, influenced by engine thrust differences and airflow disturbances around the damaged tail. Inside the cockpit, the transition was experienced not as a single event, but as a cascade of anomalies. Control inputs produced no response. Warning systems illuminated sequentially, reflecting the collapse of hydraulic pressure. The aircraft remained airborne, but the pilot's interface with the machine had been severed. They were reduced to indirect influence, manipulating thrust in an attempt to induce pitch and roll responses through asymmetric aerodynamic effects. The environment outside the aircraft now became a critical variable. Air density, wind gradients, and even minor turbulence exerted disproportionate influence on the uncontrolled airframe. At cruise altitude, the thin air reduced control effectiveness through thrust modulation, complicating efforts to stabilize flight. Any change in speed altered aerodynamic loading on the tailplane, further destabilizing pitch. The aircraft's mass distribution, optimized for controlled flight, now amplified instability. This phase of the event illustrates the second layer of systemic vulnerability, the interaction between environmental forces and degraded system architecture. The DC-10 was not designed to be flown without hydraulics, because such a condition was considered beyond credible design scenarios. Certification standards required survivability of certain failures, but not of complete hydraulic annihilation. The airframe's inherent aerodynamic stability was insufficient to compensate for total loss of control authority. The crew's efforts, while heroic, were constrained by physics. Differential thrust could induce limited roll and yaw by altering airflow over the wings and fuselage. Pitch control remained marginal, relying on thrust-induced changes in airflow over the horizontal stabilizer. These effects were nonlinear, delayed, and highly sensitive to airspeed. Each thrust adjustment introduced secondary consequences, sometimes correcting one axis while destabilizing another. The aircraft existed in a narrow corridor between divergent oscillation and temporary equilibrium. From a forensic perspective, this phase is critical because it demonstrates that the accident's outcome was determined not solely by the initial material failure, but by the dynamic response of the aircraft to an unprecedented systems collapse. The environment did not cause the failure, but it shaped the trajectory of the aircraft's final minutes. The airframe's interaction with aerodynamic loading, absent hydraulic mediation, exposed a vulnerability that had never been empirically tested. The anatomy of stress, therefore, extends beyond metal fatigue and structural loads. It encompasses the philosophical stress placed on design assumptions when reality exceeds modeled scenarios. The DC-10 was engineered for reliability within defined boundaries. United 232 crossed those boundaries, revealing how a single microscopic defect, amplified by time and energy, could negate an entire architecture of safety. The transition from controlled flight to irreversible failure unfolded within seconds, but its mechanics can be reconstructed with forensic precision. At the instant the fan disc fractured, the CF6 engine transitioned from a balanced rotating system into an asymmetric mass release. The remaining shaft and hub experienced a sudden redistribution of stress, but the dominant effect was external. Multiple titanium fragments exited the engine case at velocities dictated by tangential speed at the rim. These fragments did not disperse randomly. Their trajectories were governed by rotational vector alignment and casing rupture points, producing a narrowly distributed cone of debris aimed directly through the tail structure. The first fragment severed a cluster of hydraulic lines supplying System 1. The second, milliseconds later, cut through Systems 2 and 3. Pressure sensors detected rapid depressurization, but by the time cockpit indications updated, the physical reality was already fixed. Hydraulic fluid vented violently, atomizing into a mist that left no residual pressure capable of sustaining actuator force. Control surface actuators, deprived of hydraulic energy, transitioned into a passive state. Control cables remained intact, but without pressure, they connected the pilot's inputs to nothing of consequence. The immediate aerodynamic response was subtle, then catastrophic. Elevator surfaces, no longer actively positioned, responded to hinge moments imposed by airflow. The aircraft pitched upward briefly as residual trim forces decayed unevenly, then entered a slow oscillation. This oscillation, a long-period phugoid mode, began to grow because no corrective damping existed. Roll stability degraded as asymmetric drag emerged from the damaged tail section, while yaw oscillations appeared as thrust from the wing-mounted engines interacted with disturbed airflow. Inside the cockpit, the pilots of United Airlines encountered a system logic collapse. Control columns moved freely but produced no aerodynamic response. Engine instruments remained functional, creating a surreal asymmetry. Propulsion existed without control. The aircraft's inertial reference system continued to calculate attitude changes, but those calculations no longer translated into actionable corrections. This was not a partial failure or degraded mode. It was a complete severance between human input and aerodynamic authority. Attempts to arrest the oscillations through differential thrust produced mixed results. Increasing thrust on the right wing engine induced a yaw to the left due to asymmetric drag and thrust vector alignment. That yaw, in turn, altered lift distribution across the wings, producing a secondary roll. Pitch changes followed as thrust altered airflow over the horizontal stabilizer. Each axis was coupled to the others in a nonlinear feedback loop. Corrections lagged behind inputs, and overcorrections amplified instability. The structural integrity of the airframe remained largely uncompromised at this stage. The wings continued to generate lift, and the fuselage maintained pressure. The failure was not structural collapse, but functional annihilation. The aircraft was aerodynamically flyable in theory, but not controllable within the limits of human reaction time and available interfaces. The DC-10 had become a system without governors, responding only to physics. As the aircraft descended, air density increased, marginally improving thrust-based control authority. This improvement was deceptive. Higher density also increased aerodynamic loading on unpowered control surfaces, intensifying hinge moments and destabilizing tendencies. The phugoid oscillations grew steeper. Airspeed fluctuated dramatically, approaching stall margins at the top of each oscillation and overspeed conditions during descent phases. Each cycle consumed altitude and reduced the margin for recovery. The crew coordinated thrust changes with extraordinary discipline, but the aircraft's response remained unpredictable. Roll excursions required asymmetric thrust corrections that induced yaw, which then demanded counter-thrust adjustments. Pitch control was the most elusive. Without elevators, pitch depended on thrust-induced changes in airflow and the aircraft's natural static stability. Small timing errors resulted in amplified oscillations rather than damping. The moment of failure, in forensic terms, is not confined to the engine explosion itself. It extends through this entire dynamic sequence, where mechanical loss translated into aerodynamic chaos. The aircraft crossed a threshold beyond which traditional recovery concepts no longer applied. Checklist procedures offered no guidance because the scenario had never been anticipated. Training simulators had not modeled total hydraulic loss combined with high-altitude aerodynamic instability. The pilots were operating outside the envelope of certified human-machine interaction. As descent continued, structural loads fluctuated. Rapid airspeed changes imposed alternating tensile and compressive stresses on the wings and fuselage. While these loads remained within ultimate design limits, they contributed to fatigue accumulation in localized areas, particularly around control surface hinges and engine mounts. The airframe was being asked to absorb dynamic loads without the smoothing effect of controlled inputs. The final approach towards Sioux City was not a controlled descent, but a managed impact trajectory. Thrust modulation achieved a crude form of directional influence, allowing alignment with the runway environment. However, sink rate control remained inadequate. The aircraft approached with excessive vertical velocity, the result of unresolved phugoid motion and limited pitch authority. At touchdown, the right wing contacted the runway first, absorbing a load far beyond design intent. The impact sequence reflected the accumulated consequences of total system failure. The right wing failed structurally, separating under combined bending and torsional loads. Fuel ignition followed, but only after the airframe fragmented. The fuselage broke into multiple sections, decelerating violently, but not uniformly. Survivability varied dramatically by location within the aircraft, illustrating that the primary lethal mechanism was deceleration, not fire. From a mechanical perspective, the moment of failure was complete long before ground contact. The aircraft ceased to be a controlled system at the instant the hydraulic lines were severed. Everything that followed was an exercise in managing an already terminal condition. The forensic reconstruction isolates this truth with clarity. The catastrophe was not caused by pilot error, weather, or inadequate response. It was caused by a single material failure propagating through an architecture that allowed common cause system collapse. This phase crystallizes the central lesson of United 232. Redundancy without true independence is an illusion. A single failure mode, when coupled with system proximity and material vulnerability, can negate multiple safeguards simultaneously. The fan disc fracture was the initiating event, but the destruction of all hydraulic control was the decisive one. At that moment, the aircraft crossed from recoverable abnormality into irreversible loss, governed only by the uncompromising logic of physics. The forensic phase began before the wreckage cooled. Investigators arriving at the impact site were confronted not with a single failure signature, but with a debris field that told a layered mechanical story. The distribution of wreckage immediately suggested that the aircraft had not suffered a progressive structural breakup in flight. Major fuselage sections were largely intact until ground contact, confirming that the loss of control preceded, rather than resulted from, structural disintegration. This distinction was critical. It shifted investigative focus away from aerodynamic overstress or pilot-induced divergence and toward a systems-level collapse initiated earlier in the flight. Attention converged rapidly on the tail section. The vertical stabilizer exhibited penetrations inconsistent with external impact or ground deformation. Clean-edged perforations, accompanied by localized tearing and embedded metallic residue, pointed to high-energy internal projectiles. Within the wreckage of the tail-mounted engine, fragments of the fan disc were recovered at considerable distances from one another, consistent with a violent, uncontained failure. The engine casing showed rupture patterns exceeding design containment criteria, confirming that the event had released energy beyond what the nacelle was engineered to absorb. The recovery of the wreckage began hours after impact, under conditions defined more by urgency than by methodological clarity. Unlike civilian accidents governed by standardized international protocols, the forensic environment surrounding the downed F-117 Nighthawk was fragmented, politically constrained, and operationally asymmetric. The debris field extended across multiple kilometers, a spatial signature consistent with in-flight structural breakup rather than ground impact disintegration. This dispersion pattern immediately ruled out hypotheses of controlled descent or delayed failure. The aircraft had ceased to exist as an integrated structural system well before reaching the surface. From a forensic engineering perspective, the first task was classification. Each recovered component was cataloged by location, orientation, and failure morphology. Investigators prioritized primary load-bearing elements, wing spars, fuselage frames, control surface hinges, because these components preserve the most reliable evidence of stress sequence. Metallurgical analysis revealed a consistent pattern, regions of ductile deformation adjacent to abrupt fracture surfaces. This combination is diagnostic of high strain rate loading, where material transitions from elastic behavior to plastic flow and then to rupture within milliseconds. Wing root fragments were particularly revealing. The fracture faces displayed elongation dimples aligned with principal stress vectors, indicating tensile overload rather than pre-existing corrosion or manufacturing defect. However, microscopic examination also identified fatigue striations beneath the final rupture layer. These striations, invisible without magnification, confirmed that microcracks had been present prior to the engagement. They had not caused failure on their own, but they had reduced the critical stress threshold required for catastrophic propagation. In effect, the missile detonation did not initiate damage so much as activate dormant weaknesses embedded through years of operational fatigue cycles. Attention then shifted to the radar-absorbent material itself. Samples of RAM-coated panels were recovered in varying states of degradation. Laboratory testing focused on adhesion integrity, dielectric consistency, and thermal aging characteristics. Investigators found localized delamination zones where bonding strength had fallen below specification. These zones corresponded closely with areas exposed to maximum aerodynamic heating and vibration during routine flight. While this degradation had negligible impact on structural strength under normal loads, it altered the mechanical response of the skin during blast exposure. Without the damping effect of intact coatings, vibrational energy transmitted directly into the aluminum substrate, amplifying stress concentrations at fastener interfaces. The missile's influence was reconstructed through fragment analysis and blast modeling. Shrapnel penetration patterns were sparse, confirming that proximity detonation, not direct impact, was the primary damage mechanism. High explosive residue analysis matched the warhead composition associated with the S-125 NEVA. The distribution of blast damage suggested an engagement geometry offset from the aircraft's longitudinal axis, consistent with asymmetric impulse loading. This asymmetry explained the immediate rolling moment observed in reconstructed flight dynamics. Investigators simulated the blast interaction using finite element models calibrated with recovered material properties. These simulations demonstrated that even without fragment penetration, the overpressure alone was sufficient to exceed yield stress in multiple skin panels simultaneously. More importantly, they showed how the aircraft's faceted geometry intensified local loading. Flat surfaces oriented normal to the shock front experienced impulse amplification relative to curved geometries. This was not a design flaw in isolation. It was a predictable consequence of prioritizing radar scattering over blast tolerance. The flight control system became a focal point of analysis, not because it failed electronically, but because it functioned precisely as programmed. Data recovered from onboard memory units indicated that control laws responded aggressively to sense deviations. Actuator commands reached maximum deflection rates within milliseconds. However, structural damage altered the effective stiffness of control surfaces, invalidating the assumptions embedded in the control algorithms. In engineering terms, the system entered a regime of model mismatch. Control actions based on an intact airframe accelerated failure in a compromised one. This finding underscored a critical limitation of fly-by-wire architectures when structural integrity is no longer guaranteed. Human factors analysis played a minimal role in the conclusions, not because the pilot's actions were irrelevant, but because the event unfolded faster than meaningful intervention could occur. Ejection timing was consistent with survivability thresholds derived from structural breakup models. There was no evidence of delayed decision-making or procedural deviation. The aircraft transitioned from nominal flight to unrecoverable disintegration in a time frame measured in seconds, well below the window in which training or experience could alter outcome. The investigative findings challenged several doctrinal assumptions. First, they demonstrated that stealth effectiveness is not binary but conditional, dependent on maintenance state, environmental context, and adversary adaptation. Second, they exposed a systemic vulnerability, the lack of structural redundancy proportional to the aircraft's perceived survivability. The F-117's design philosophy assumed avoidance of engagement as the primary defense. Once that defense failed, the aircraft possessed no secondary layer of resilience comparable to conventional combat aircraft designed to absorb damage and remain controllable. Material scientists involved in the investigation emphasized that none of the failures observed were anomalous. Aluminum alloys behaved as expected under high strain rate loading. Adhesives failed where shear stresses exceeded bond strength. Fatigue cracks propagated along known paths. The catastrophe was not the result of unknown physics, but of known phenomena intersecting simultaneously. The aircraft was operating exactly at the edge of its design envelope, not in terms of performance, but in terms of survivability assumptions. The political sensitivity of the program limited public disclosure, but internally, the conclusions were unambiguous. The loss of the aircraft did not indicate that stealth was ineffective. It demonstrated that stealth alone could not be treated as an absolute shield. Survivability had been reduced to a single pillar. When that pillar cracked, the structure collapsed without resistance. Investigators also noted the operational context. Repeated use of identical flight routes had reduced the randomness upon which stealth doctrine implicitly relied. This predictability transformed probabilistic detection into a cumulative certainty. Over time, even weak signals became actionable through correlation and persistence. The forensic record made clear that the engagement was not a technological upset, but a methodological one. The adversary did not outpace stealth, it waited for it to become routine. In the final synthesis, the forensic narrative converged on a systemic explanation. The aircraft was not defeated by an old missile in isolation. It was defeated by the convergence of material aging, fatigue accumulation, geometric compromise, environmental variability, and operational predictability. Each factor alone was manageable. Together, they eliminated margin. The wreckage, laid out in controlled facilities and analyzed piece by piece, told a consistent story. There was no evidence of sabotage, no manufacturing defect, no maintenance lapse sufficient to explain the loss independently. The failure resided at the intersection of design philosophy and real-world complexity. The aircraft had been engineered for a specific threat environment. That environment had evolved, and the design had not. This forensic phase closed not with blame, but with recognition. The aircraft performed as designed. The missile functioned as intended. The failure occurred at a higher level, where assumptions about invisibility replaced considerations of damage tolerance, and where statistical safety margins were mistaken for guarantees. The consequences of the shoot-down did not manifest immediately in public doctrine, but within engineering circles the impact was profound. The event forced a reassessment of how survivability was conceptualized in the stealth era. The loss of a low observable aircraft to a legacy air defense system did not invalidate stealth as a concept. It exposed the danger of treating stealth as a substitute for resilience rather than a complement to it. From that moment forward, invisibility could no longer be regarded as a terminal advantage. It became a variable, powerful, but finite. One of the first systemic shifts occurred in materials engineering. Designers acknowledged that radar-absorbent coatings could not remain passive, sacrificial layers. Subsequent platforms incorporated composite skins where electromagnetic attenuation and structural load-bearing were integrated rather than separated. This reduced reliance on thin metallic substrates whose failure characteristics under blast and fragment loading were well understood and poorly forgiving. The lesson was explicit. Material failure modes must be considered not only under aerodynamic loading, but under hostile impulse environments. Structural redundancy, long deprioritized in stealth-first designs, returned as a central requirement. New aircraft architectures distributed load paths more diffusely, ensuring that localized damage would not precipitate immediate global failure. Designers accepted modest increases in radar cross-section in exchange for improved damage tolerance. This was not a retreat from stealth, but an evolution toward balance. Survivability was reframed as a layered system, low observability, electronic countermeasures, and structural robustness operating together rather than in isolation. Flight control philosophy also changed. The incident demonstrated that fly-by-wire systems optimized for unstable but intact airframes could become liabilities once structural assumptions were violated. In response, control laws grew more adaptive, incorporating failure detection logic capable of reconfiguring control strategies when sensor data suggested loss of stiffness or continuity. The goal was not to save an aircraft already beyond recovery, but to delay divergence long enough to preserve pilot survivability and, in some cases, limited controllability. Operational doctrine underwent quieter but equally significant revision. Predictability was reclassified from efficiency to exposure. Mission planners reduced route reuse, varied altitudes and timelines, and emphasized stochastic unpredictability as a defensive measure. Stealth platforms were no longer treated as immune corridors through hostile airspace, but as assets whose advantage diminished with repetition. This shift acknowledged an uncomfortable truth. Adversaries do not need to defeat stealth technologically if they can erode it statistically. Air defense analysis absorbed parallel lessons. The engagement validated the continued relevance of low-frequency surveillance systems when integrated with patient, disciplined tactics. While such systems could not provide precise targeting data, they could create situational awareness sufficient to cue other sensors or enable opportunistic engagement. The broader implication was that technological obsolescence is contextual, not absolute. Systems dismissed as outdated can regain relevance when matched against adversaries optimized for different threat spectra. Stealth aircraft that followed incorporated these insights explicitly. Platforms such as the B-2 Spirit and later the F-22 Raptor integrated composite structures where skin and structure were inseparable. Damage tolerance testing expanded to include blast and fragment scenarios previously considered improbable. The emphasis shifted from avoiding detection entirely to surviving partial detection long enough to exit contested airspace. This reframing acknowledged that perfect invisibility was neither achievable nor necessary. Maintenance philosophy evolved as well. Aging effects on stealth materials were treated as survivability variables rather than cosmetic or performance issues. Inspection regimes focused more heavily on detecting subtle delamination and bonding degradation that could influence failure behavior under stress. The goal was not to preserve radar cross-section at all costs, but to maintain predictable mechanical response. In other words, engineers prioritized knowing how an aircraft would fail rather than assuming it would not be tested. At the doctrinal level, the incident eroded the myth of technological finality. Air power strategists recognized that adversaries adapt asymmetrically. Instead of matching stealth with stealth, they exploited cost-effective counters rooted in physics rather than innovation. This realization influenced procurement decisions and threat modeling across multiple domains. Systems were evaluated not only against state-of-the-art opponents, but against disciplined use of legacy capabilities operating outside expected paradigms. Philosophically, the shootdown marked a boundary between eras. The early stealth age was defined by secrecy, novelty, and overwhelming advantage. Its aircraft were conceived as answers to known problems, optimized against specific detection methods. The post-incident era accepted uncertainty as a design constraint. Engineers began designing for the unknown, acknowledging that future threats would not resemble past ones, and that survivability margins must absorb surprise as well as force. The event also reshaped the conversation around progress itself. Technological advancement had been framed as a linear trajectory toward dominance. The loss of the aircraft demonstrated that progress is cyclical, marked by periods of advantage followed by adaptation and counter-adaptation. Each leap forward carries with it new vulnerabilities, often invisible until stress reveals them. This is not a failure of engineering, but its natural consequence. In retrospect, the aircraft did not fall because it was obsolete, nor because its adversary was innovative. It fell because its design assumptions were too narrow for the environment it encountered. The system worked perfectly within the boundaries it understood. It failed precisely at the point where those boundaries ended. That distinction matters because it reframes the event not as a humiliation, but as a data point, expensive, irreversible, and invaluable. The legacy of the shootdown persists in every modern survivability analysis. It serves as a reminder that engineering excellence does not confer immunity from physics, and that dominance achieved through specialization must be protected by humility. The cost of progress is not measured solely in development budgets or program timelines, but in the willingness to accept that no system, however advanced, operates outside the reach of material limits. Stealth remains a cornerstone of modern air power, but it is no longer treated as an invisibility cloak. It is understood as a reduction in probability, not an elimination of risk. That distinction, forged in a night sky over Serbia, continues to shape how aircraft are designed, how missions are planned, and how engineers think about failure. The aircraft's loss did not end an era. It corrected it. In the final analysis, the shootdown stands as a case study in the discipline of engineering realism. It demonstrates that survivability emerges not from any single innovation, but from the integration of materials, structures, systems, and doctrine, all designed with the expectation that assumptions will eventually be tested. When they are, only those systems built to endure surprise remain intact.